Welcome back to the final chunk of talks on the final day of PyCon UK 2022. Woo! So our first talk in this chunk of talks will be by Eli Holderness, and their talk is Pointers in My Python. It's more likely than you think. Please give them a big hand.
All right, let's get cracking. In today's talk, we are going to be talking about three things. First is what pointers are and where you'll find them in your code. Second, we'll talk about what the ID of a Python object is and how it relates to ideas of equality in Python. And finally, we'll talk about how CPython in particular can tell when you're done with an object that's in memory and what happens next. So, what is a pointer? Well, pointers point at objects. Here's an example. Here's an object, and here's a pointer to it. But this isn't the only kind of pointer that we might have to it. I'm also, unfortunately, on Twitter. I also have a Hebrew name, and being helpfully cut off by the end of the screen there. And I also can be known by many other names. What does this actually mean for Python, though? Well, Python has a namespace, which is the entries in the namespace are like names of variables. They're things that when you type them into your interpreter, Python knows what you mean. And you also have objects in memory, and pointers are the entries in the namespace that correspond to objects in memory. We can actually take a look at the namespace of Python. We're only going to be considering the global scope today, so no need to worry particularly about that, scopes. We can take a look at the namespace. So let's say I've fired up my Python interpreter and I've defined a couple of variables, nothing particularly exciting. I can inspect the namespace by calling this built-in globals function, and it will print me out a dictionary with lots of things, and at the end will be the things that I have defined. So that's what the namespace is. It's something that people will be familiar with, even if they've not heard about it talked in that term. So, for a lot of the examples that I'm talking about today, we'll use lists, and lists are useful because they are objects in memory that can contain other pointers. And this makes them very useful for illustrating some unusual or unexpected behaviors that Python has as a result of using pointers. So, let's start with pointer aliasing, which is also known as that phenomenon when a variable changes and you didn't quite expect it to. So, we're going to be using lists as an example. Here I've defined a list A with some strings in it. Defined it, printed it out, so far so good. Let's say I want to make a new list called B that's very similar to A. So I say, well, I'd like to start with A, so B equals A. But actually, instead of my cool list, I'd like it to be my awesome list. So I change the second element of my list B. So far so good. But then when I go back and look at list A, you can see that that one has changed too. And if you are new to Python, you might not be expecting this. Well, I changed B. What's happened? Why has A changed as well? And this is because B and A are actually pointing at the same object. We can get around this. If we want to make a completely new list, we can use the copy method on a list. And what that does is it actually makes an entirely new list object. So instead, let's try this again, changing the second element of that list. And when we look back at A, we can see that that change did not affect our original object. So when we used the copy method, it actually created a new object to point to, and you didn't have two pointers pointing at the same object. So I heard you like pointers, or at least I hope you do, because you're here listening to me talk. What if we had a list within a list? Now, this is what we're defining here. You can see the double sets of square brackets. You've got a list, and it's got one element, which is itself a list. And we're going to do what we did at the end of the last example and use the copy method on that list. We're going to say, okay, I want a new list, and I want it to be the same as A, so I'll use that copy method that we used last time, did what we wanted. And I actually want to append the name Charlie to my list of names. So I go and I access the first element of my list, which we know is the list that's inside that, and we append something to it, and this does what we expect. But if we go back and look at the first element of A, that has also changed, even though we use the copy method. And this is because copy will copy the outer object and make a new version of that. but it will copy the pointers within that object, and those pointers, one level lower, point at the same object, which is that inner list. So what if it's pointers all the way down? How can we avoid this pointer aliasing behavior? Well, there is a solution, because Python is amazing, and it is called deep copy. So from the copy module in the standard library, you can import this deep copy function. And what deep copy does is it copies things all the way down. So if we now try again, a new list, we want to say, I want to start again, copy my list A, but I'll do a deep copy this time. And then we do the same thing again. We append an element to that inner list, and you can see when you print out that inner list from C, it's done what we wanted. And if we then go and look at the inner list of A, we can see it hasn't changed. And that's because it created a new version of that inner list as well as the outer list. We can see a visual representation of this. So when you use equals, if I say B equals A, it just points to the same object, and anything, obviously, that object points at is going to be the same. If I use copy, it makes a new object at the first level. But if that object has pointers, those pointers will secretly underneath still point to the same things like a list within a list. And then deep copy does what we just saw, makes new copies of all of the objects all the way down with no pointer aliasing. You might think that deep copy is always what you want to do, but maybe of working in a situation where you've got some memory constraints and actually you don't want to have multiple copies of the same objects if they don't actually need to be separate. So you have options, basically. And hopefully you can go forth and write code and understand what's going on with your pointer aliasing when you understand the difference between these things. I promised you some tuples behaving badly in the abstract. So tuples, for those who are not familiar, are essentially, they're like a list, but they're immutable. And that means that when you create a tuple, the things that, its elements cannot change after it's been created. Those elements, though, can be pointers. So let's say we've got a tuple of one element. If that first element is a pointer, it can't change, so it has to point to the same object during the lifetime of the tuple. But if the thing it points to is mutable, we can end up with some odd behavior. And we'll see exactly what this is. Here I'm defining exactly that, a tuple with one element, and that element is a list. And this is fine and good, we can do that. And if I want to, I can append something to that list that lives within my tuple. You can see this is perfectly normal Python, this is all well and good, nothing unexpected here. This isn't the only way that you can add an element to a list in Python, though. We could also use the plus equals operator. And that looks like this. And when you do this with a list, it looks very much like appending. You expect that object to be appended to the end of your list. But if we try it with our tuple example, we get this. You cannot assign to elements of a tuple. That makes sense. They can't change once the tuple has been created, right? And you are saying this should equal something new, right? And so far, this isn't actually that surprising. But what is surprising is if we go and look at A0 now, that number 5 has been appended. So what is going on here? Because this is actually really quite confusing unless you know what is going on under the hood. And what is going on under the hood is that the plus equals operator does two things. First, it creates a new object that is the sort of the target object that you want. And in our case, this is a list that has that number 5 at the end. Because lists are mutable, it can do this in place. And that's why when we go and look at A0, it's done it in place. But not everything is mutable. If we were doing this with strings, it would need to actually reassign the original pointer at the new object. And that's what the equals does. And it does that whether or not the objects it's working with are mutable. So it's actually trying to assign to that pointer when it doesn't need to, but that's why we get that error. So you try and do this thing, Python says, no, you can't do it, but I did it. So I would like to come back to this situation. We have two pointers that are pointing to the same object in memory. And this is the root of the pointer aliasing behavior, is when this happens and you do something to B and it's actually changing the element that A points at as well, the object. Now, sometimes you will know that this is the case, and sometimes you won't. How can you tell when two objects, or two objects you think are different, might actually be the same? And this is where object IDs come in. And we're going to take a bit of a detour to explain what object IDs are. So Python has this built-in function. You can call it on any object, the ID function. And it has these properties. The ID of an object is unique for all objects that are in memory. The ID of an object must be constant during the lifetime of that object, as long as that object is in memory. Its ID will be the same. But only for the lifetime of X. If I have one object and it has an ID, and that object is removed from memory, a new object might be created and have that same ID. But that's okay, because the old one doesn't exist anymore. And many implementations use the memory address of an object for this because it has all those properties. This isn't necessarily possible for all implementations of Python. CPython does it. But Sculpt, which is a Python to JavaScript transpiler that we use at Anvil, generates and caches a random number because it's built on JavaScript, which does not expose stable object IDs. For these examples, we'll be looking at CPython. So, it's probably what most people are familiar with, but that's kind of just a detail of this talk at this point. So we have our list, and we're going to look at the ID of it, and it prints us out this big, long number. For anybody who does code in C, this would probably look much more like a pointer to you if it was in hex format. And if we have our example where we set B is equal to A, creating a new pointer to that same list object, we can look at their IDs and we can see they're the same. So that's one way to see that these two pointers are pointing at the same thing. To further illustrate this, we can take the copy of A, which we know creates a new object, and when we look at their IDs, they are different. This is what we should expect. So in order to actually use this in code, it's really clunky to be calling the ID function all the time. We can use the comparator, is. We can say, if A is B, then that's exactly equivalent to their IDs being the same. And this is how is works in Python. That's what it does. It takes the IDs and it compares them. But it makes for much more human-readable code. So if we look at our example, the familiar example where we've got A as a list, B is another pointer to that list, and C is a copy of that list, a new object, then we can look at A is B is true. They have the same ID. And A is C is false. They have different IDs. This isn't the only way that Python lets you compare objects, though. We also have the double equals comparator that looks like this. And if we try it with these three objects, rather, we can see A is equal to B. That's true. But A is also equals to C. So it's doing something different than is. And the reason for this is that the double equals comparator uses the double underscore equals method, or dunder method. And this is a method that is defined on Python objects, allowing them to be compared. So what actually is that equals method? Well, it's double underscore method. If you have a Python class, it will have dunder methods like this, like string, you may be familiar with, which you can moderate. You can override to define how the string built-in function behaves on a given object of that class. You've got the del method, which we'll look at a bit later. It's called when an object is about to be removed from memory. And init, which I imagine people will be quite familiar with, and double underscore equals is one of these. So what that does is it defines how that comparator behaves. If you've defined a double underscore equals method, when you call the double equals comparator, it will behave in the way that you have defined in that function, in that method. One thing we could do is we could define a class and override its equals method to just use the other comparison that we have, the is, and only return true if the two things have the same ID. This is actually the default behavior for any user-defined class in Python. We could also do something like this, my named class, which takes a name so we can differentiate objects that we've got. And I've here defined its equals method to just indiscriminately return true. And this, I heard a bit of laughter. Yes, you don't want to do this. It leads to behavior like this, where I've got two different objects. They are clearly not the same. They've got different names. But they compare true, because that's what we told the double underscore equals method to do. You might go the other way and have a unique class, and it just indiscriminately returns false. This is good. Two objects that aren't the same will never erroneously compare true, right? But it won't compare true to itself either. So that is how the is and double equals methods of equality work in Python, why you might want to use them in different situations. Perhaps you want to define some method of equivalency between objects that is somewhere in the middle, and you can do that by overriding this double underscore equals method. Right. Object lifetimes. When we talked about the ID of an object, we talked about objects having lifetimes, living in memory only for a certain amount of time. This is because your Python interpreter only has so much RAM available to it. You don't want to clog it up with things that aren't usable anymore, aren't useful. And there are a couple of ways that Python frees objects from memory. You've got reference counting, and you have garbage collection. And this is true as of Python 3.11, I believe. I hear whispers of something changing in this direction in the future, but we'll have to see. And the first one we're going to talk about is reference counting. And reference counting works in the following way. The Python interpreter will keep track of how many pointers you have pointing at each object. So if you think about that slide at the beginning with my face on it, there would be 4 references to me, right? It was my name, my Twitter handle, my Hebrew name, and that Anvil DA with blue hair, right? So Python keeps track of how many such things there are. And then if that number reaches 0 for any given object, we can no longer get at it, right? From the namespace, we can no longer reach it. And that means that object must be useless. There's no way to access it, so we might as well free that memory. And we can see this in action. What we're going to do is we're going to override another double underscore method, the del method. And this is called when an object is about to be removed from memory. It does not itself deal with the removal from memory, but it's called right before, the last thing that Python does before it frees that memory. So we're going to be using this class, my named class. It takes a name so we can differentiate objects that we've got. And it will then print right before that object is about to be removed from memory. It will say, I'm going to delete this thing. So this is going to give us a little bit of insight into what's going on. And we can invoke this reference counting method of object removal. You've got Dave, who is my class Dave. And if I delete him, he is deleted. This is what we expect. Perhaps not very kind, but, yeah. We can also see this in action when we have more than one pointer to the same object. I've got Alice, and then I make another pointer to Alice. I give her a second name, unimaginatively, also Alice. And if I then delete Alice, her first name, we don't get that print output because there's still a remaining reference to Alice. But if we delete that reference, then we get that print output that we're expecting. However, what if I have a reference that is a cycle? If I've got objects that point at each other? We can see how we can set up a cyclic reference. Going back to looking at the namespace, where we can look at the namespace and we can say, is something in the namespace? And we're going to be using this to check whether or not an object has a pointer to it from the namespace, has an entry. And you can do this by saying, well, is this thing in globals? And it says true or false. So I'm going to make 2 instances of my named class. I've got Jane and I've got Bob, and they are friends. We can assign attributes at runtime in Python to arbitrary objects, and I've done this. Bob now has a pointer to Jane, and Jane now has a pointer to Bob. They are now a cyclic reference. And we can see that both of their pointers from the namespace are still in the namespace. Jane is in globals, and Bob is in globals. But then, if we delete those pointers from the namespace, if we just had the objects on their own and we hadn't made them point at each other, at this point, their reference counts would fall to 0, and they would be deleted. But we don't see that. They have a pointer to each other still. They both have one reference, even though neither of them can be reached from the namespace anymore. As a unit, this cycle is useless, but it cannot be deleted by reference counting because it still has references within it. So a visual representation of what's going on here. You've got your 2 objects. I've created them. I've made them point at each other. And then I've removed the entries from the namespace that allowed them to be accessed. And reference counting won't delete them at this point because of those orange arrows, even though there are no connections left from the namespace. So reference counting is not sufficient. If we create lots of cycles and then isolate them, turning them into cyclic isolates, then eventually our Python's working memory is going to get clogged up with all these things. We need a better solution. And this is where CPython's garbage collector comes in. And from here on, we'll be focusing specifically on CPython. So CPython's garbage collector is designed to deal with cyclic isolates. And the way it does that is it detects them, and it calls the finalizers of all those objects. So it says, okay, well, I need all of these objects to clean themselves up. The del method is often used for closing files that were opened at object creation time and things like that. I need all these objects to clean up after themselves. And finally, it'll go around and it'll break those cyclic references. It will remove the pointers, at which point the reference counts will fall to 0, and reference counting can mop up. We can look at the garbage collector, and the garbage collector keeps track of objects in Python. It won't keep track of strings, because they can't contain pointers. They can never be part of a cyclic isolate. But it will keep track of things that can contain pointers, like a list. So any arbitrary Python object will be tracked, because it can contain pointers. We can set attributes on it at runtime. So the garbage collector, in order to detect cyclic isolates, it can traverse pointers. It can follow them around, and this is the way that it can detect cycles. You can see all the things that my list refers to using this getReference method on the garbage collector. And you can also, when it sets up a cyclic isolate, it will be able to detect that. So here we are setting up a cyclic isolate. And just as we did before, Jane and Bob exist, they're friends, and now they have no names. And what we can do to rectify this situation is we can actually force the garbage collector to do a collection run, where it does that behavior of detecting the cyclic isolates, calling the del methods on them, and removing the references, and at which point reference counting kicks in. We get the print statements that we expect. Jane and Bob have been removed from memory. And that number 4 at the end is the number of objects that have been removed from memory by this operation. Jane and Bob are objects, and each of them had a name that was a string. So that's why we get 4 there. So there's a caveat to this, which is that when the del method is called on an object, it doesn't actually guarantee that after those del methods are called, the cycle will remain isolated. And obviously, if the cycle is no longer isolated after that step, it's not safe to remove them from memory because perhaps somebody is depending on them somewhere. So let's do that. Let's do some inadvisable things with finalizers. Here we have my bad class, and it has a name. And in the del method, it has that print statement right at the end, but before it does that, it creates a global variable. It reaches back out into the namespace, creates a new pointer, and points it at itself. So with this bad class, let's set up a cyclic isolate, just like we did before. And if we call garbage collection on this, it will call their finalizers, at which point those print statements will run, but we get 0 at the end. No objects were removed from memory. And this is because during the execution of those del methods, they reached out into the namespace and created a new pointer. The cycle is no longer isolated. We can't get at it from Jane and Bob. Those have been deleted, but that global person variable exists now in the namespace, and it allows us to access those things. And for that reason, garbage collector cannot remove those references and delete those objects. If we actually go and look at that person object, you can see that it's Bob. Going back to here, Bob was the second to have its finalizer called. So that is the most recent object that the pointer from the namespace was assigned to. So if we go and look at that person, we can see it's Bob, and we can access Jane through person.friend. So does this break garbage collection entirely? Fortunately, the answer is no, because the people who write Python are very clever. The del method, this is the visual representation of it reaching out into the namespace and creating that new person variable. The del method on an object can only ever be called once, precisely to prevent issues like this. If we, we can see that Jane is not in the namespace, but what we can do is we can delete the new pointer, person. And now if we run the garbage collection, those 4 objects are removed from memory. We don't get the print output because the del methods are not being called again. But we are freeing the objects from memory and removing the problem where our interpreter's memory will get clogged up with cyclic isolates left, right, and center. If you are writing code where you find that you actually are creating a lot of cyclic isolates, you might want to pepper a few GC collects into your code. I don't know if this is good or bad practice, but it might speed things up. All right, so what have we learned? We've talked about where you'll find pointers in your Python and the sometimes unusual or unexpected behaviors that you can see as a result. We've talked about why is and equals are different and how they work, why you might use one or the other. And finally, we've talked about how objects are removed from memory and how you can do some, inadvisable things to mess around with that process. That wraps up this talk. Thank you so much for your attention. I will have some time for questions.
Thank thank you very much. Thank you very much for that great talk. Do we have any questions?
Hi, lovely talk.
Thank you.
Does everything you described about globals also apply to lower namespaces inside functions and how they, like a variable that's created inside the function will come to its unfortunate demise?
Yes, so my understanding is, and I have not yet written my talk on scopes in Python, so I could be wrong here, is that when you define a variable within a scope, when you leave that scope, that reference no longer exists. And so if you've created a cycle and then moved out of scope, I think that would create a cyclic isolate. And that, if that's true, that's probably one of the most common ways that they're created in code. So with scopes in Python, you sort of pointers only exist for the lifetime of that scope, which might be the duration of execution of a function or something. There's definitely more depth you can go into about when you include things like scopes. There's a reason I limited it to the global scope for this talk, otherwise I'd be here all day. Does that answer your question?
Okay, any more questions? Okay.
Hi, thanks for your talk. Very interesting. So why was the Dell dunder method not called again when you did Dell on person in the global namespace? Is it like Dell was only called once on like the
Exactly.
instant?
Yeah.
Okay, yeah.
I don't actually know. I woke up in a cold sweat last night wondering, if you called copy on the object at that point, does it copy the status of whether or not the del has been called? So I'm going to go away after this and fire up my interpreter and do some cursed things. But yes, the del method for a given object in memory should only be called once, precisely to prevent objects sort of keeping themselves alive in this way. If you do genuinely need to do something in the del method that causes garbage collection to abort at that point, you probably know what you're doing. You know that that is actually what you need to do, a bit like meta classes. Don't use them unless you absolutely know that it is correct. If you are mucking around with the del method and you don't know that it's only ever going to be called once, you should not be mucking around with the del method. Yes, per object, only once, for the purposes of not breaking garbage collection.
So is it like the del keyword decrements its reference count, and if the del dunder method hasn't been called on it, it also does that?
Very possibly. I have not actually gone and looked at that I would go and look at it in CPython. It's entirely possible that it just has a count of 1 that gets decreased and you're not allowed to do it again. That I think is sort of implementation detail. I don't think that's part of the spec necessarily.
All right, thank you.
Yeah.
Thanks.
But take that with a pinch of salt because I haven't looked it up.
Okay, thank you for those very interesting questions. Maybe a follow-up tweet. We can find out about those remaining details there.
Yes, absolutely.
Let's thank Eli once again for her great talk.